Okay, good afternoon, class. Today is lecture 5 of Introduction to Nanoscience and Technology. Today we'll talk about the quantum and just touch very the surface or basics and then go into the review of some of the chemistry that you have learned in high school level. So, as I have briefly mentioned at the end of last lecture, the quantum mechanics is the science of the very small. So the quantum is originated from the word quanta, right? You know the word quantity, right? Basically, quantum or quanta is the minimal unit of a given substance or any substance, right? Quantum is the minimal size or unit that consists a lot of substances. So, such as electrons, photons, or phonons, right? We all have learned about this concept at the very end of last lecture. Okay. Okay. So it explains the interactions with energy on the scale of atoms and subatomic particles. And in a very small system, we have learned that particles can behave like waves. Okay. So yeah, I mean we learn about this photon, oh, 오케이. 네. 감사합니다. 네. 오케이. 오케이. 잠시만요. 그 소리 좀 끌게요. Give me a second. Okay. Okay. So yeah, so photon, electron, and phonon, right? Okay. At a small scale, we have to care these individual particles, okay? Because in nanoscale, all these atomic behaviors or interaction with these atoms and these electrons or phonons, right? It becomes very, very important, right? If it's a really big scale, then we can just take the average, right? But in a small scale, we have to care about all these single interactions at a time. So let's talk about light, all right? I think I also covered this lecture, right? I said that light is an electromagnetic wave. Okay? And depending on its wavelength or frequency, its energy changes. So these wave property, the speed of light is same. However, their wavelength or frequency are different, and all these property determines their energy property and so on. Okay. So when we talk about this quantum mechanics, there is a very important concept called the wave function. As I said, in a very small scale or in a quantum regime, right, I said that all the particles or electrons, photons, phonons, or even molecules, right, that they can be treated as particles. And these particles travel like a wave. Okay. So in high school physics, we learned the concept of momentum. Does anyone remember the equation for momentum? 모멘텀식 기억나시는 분 있어요? 그죠? 네, 맞죠? 그쵸? Momentum equals the mass times velocity. Okay? Okay? Right? So if a substance have a mass, non-zero mass, and non-zero velocity, then that material or that substance has momentum. It is the same case for all these small particles. Right? We know electron has we know the electron has mass, right? Photon, right, is also a particle, so it has a mass at certain velocity, right? So all these particles has a momentum. So let's say this momentum is p, right, with a wavelength of lambda. We know that the wavelength is right. This one cycle, right? This length is wavelength, right? Okay, right. And the inverse of this wavelength is frequency. So when the wavelength is long, frequency is low. When a wavelength is small, then the frequency is high, right? I mean, we all learned this in undergraduate level, right? So if we consider that the certain particle has a momentum p in wavelength lambda, right, then actually we can calculate the energy of that particle using this wave function developed by this person. So this is the definition, right? We know the momentum is mass times velocity, right? So we can also do the very similar thing to the energy. So the energy E contained in photon, which represents the smallest possible packet of energy in an electromagnetic wave. So if you have many photons, or if you have a high light intensity, that light possesses very high energy. The smallest unit that light can present or light can exist, 가장 작은 단위로 빛이 존재할 수 있는 거는 single photon입니다, right? Okay. So this single photon energy is the smallest possible energy in light or electromagnetic wave. It is directly proportional to the frequency f according to the following equations. Okay, so wavelength lambda equals h divided by momentum. So you must be thinking, okay, what is h? Okay, h is the Planck constant. 이건 그냥 상수예요, right? Discovered by Planck. Okay, so Planck did a very short experiment. I believe this experiment was explained in your reading assignment, right? He did very short experiment. He measured this momentum, or he tried to measure this momentum of single. I believe it was a hydrogen molecule, right? Or some other gas, right? So he did this experiment, and he did this line fitting and got this Planck constant. Basically, this constant has a unit of joules times second. Okay. Right. So if you divide this Planck constant by the momentum of this photon particle, then you can get the wavelength. So this equation relates wavelengths and momentum. Again, we know that the Planck constant is the fixed value. So this means that lambda is inversely proportional to 1 over momentum. Okay? So if particle has low momentum, it'll have long wavelength, and if the particle has high momentum, it'll have low wavelength. So okay, let's say, well, maybe let's say, okay, this part is somewhat done. Okay, then let's talk about the energy. We can also connect this to energy. Energy is equal to Planck constant times speed of light divided by wavelength. Okay. From above, P equals h lambda, right? So if we actually plug in this, we know that, energy of photon is momentum p times speed of light. So from here we can get the energy of the photon is directly proportional to the momentum, right? And is also inverse to the wavelength. Okay, so this is the relation. So what does this mean, right? How this makes sense? I mean, in nature, or we learned from the thermodynamics, we know when molecules or when atoms, when they gain energy, right? Right, they start to vibrate or their temperature goes up. So there is something, right? So there is a change in kinetic energy, so they move faster, right? Or their internal energy goes up, which converts into the increase in temperature. Okay, all right. Okay. So this very similar concept is also happening in a quantum regime. So here, using this equation, we can quantify the energy of the wave. We can quantify of the light if we know their wavelength or resonating frequency. And also the Planck's constant, symbolized h, relates the energy in one quantum, photon of electromagnetic radiation, to the frequency of radiation. Okay? Okay. So every light travels in the same speed. Their velocity is same. However, right? So in kinetic energy, right? In kinetic energy, we know that kinetic energy equals mv squared, right? Okay. But in case of light, the speed is the same, right? Right. However, there is a difference in internal energy of these photons, and this difference in internal energy is converted into the difference in their wavelength or frequency. This concept can be a bit overwhelming, especially in this online lecture system. Right? But I mean, there are plenty of YouTubes, or you can come to my office, or you can call me, or you can ask me questions for a more detailed explanation to understand this concept. I believe for many of you, or at least for some of you, you guys are already aware of this concept, right? And maybe you are wondering that, oh, why is Professor Kim spending too much time in this single slide? Okay. But for some of you who's not familiar with this concept, right? I mean, I hope that you understand this concept, and I believe that you probably had heard about this Planck constant, right, or wavelength frequency concept. Okay, all right. So when we talk about this nanoscale, right, we always talk about photons or electrons, right, interactions. Right? So let's say, okay, let me write this down. So in nano, right, electrons or photons, right, carries energy. I mean, of course, in bulk, in micro, or in macro, right? Electrons and photons also carry energy, right? But what I'm trying to say is that in nano, everything scales down and they become comparable to the size of electron behavior or photon behavior. 그러니까 어떤 물체가 나노로 굉장히 작아지면 일렉트론 하나의 움직임 혹은 광자 하나의 움직임 또는 에너지 이런 거에 굉장히 영향을 많이 받기 때문에 okay, we can consider the electron and photons as a major energy source or energy carrier in nanoscale. And when we talk about these values, right, we use this concept of electron volt. In a bulk scale, we just use volt. But in nano or in a semiconductor physics, we use this terminology called electron volt. So what is this? It is a unit of energy equal to approximately 1.62 10 to the minus 19 joules. So it is a very, very small. Okay. Yeah, I'm sorry. My tablet and my PC, my pen, something is there. I think there is some delay, but anyways. So amount of energy gained by the charge of a single electron moved across the electric potential difference of 1 volt. Okay. So if there is a single electron traveling a 1 volt potential difference, right? Since there is a potential difference, this electron will gain charge energy. And that amount of charge energy is equivalent to 1 electron volt. So it is 1 volt times 1 electron charge. So this unit is used to express photon energy, electron energy, band gap, right, and many concepts. Right? When we explain photo optoelectronic energy conversion, photovoltaics, right, a lot of this energy unit is in electron volt, not in volt. Okay. Okay. So, so I said that light has different colors. Of course, ultraviolet or infrared, beyond that regime, we cannot see it. Our visual conception, our visual perception, or the 뭐 시각, 뭐 시력의 감각, right? It has a range of color that it can detect. So now we have learned this concept. So again, we have learned that, oh, now we can calculate this energy of light is equal to Planck constant times speed of light divided by wavelength. Here, speed of light divided by wavelength basically gives you the frequency. or here symbol. If you divide the speed of a wave by the wavelength, you get the number of oscillations per second, or number of oscillations per unit time. And that is the definition of frequency. Okay? And also we use the unit of hertz. And the wavelength is on the order of meters. Okay? All right. So depending on the light wavelength, their color is different. So is there anyone who uses the laser for their research? 혹시 연구를 위해서 레이저 쓰시는 분 있어요? IC의 뭐 권혁준 교수님 방 학생들이나 아니면은 저희 전공의 뭐 한상현 교수님 방 학생들이나 안 계신가요? Anyone who uses laser for their research? 아, 네. 어떤 레이저 쓰세요, 영재 학생? What kind of laser do you use, 영재? Okay, so Youngjae is using 1550 nanometers laser, which is infrared regime. Okay. If you use some of the characteristic tools in our school, such as Raman microscope, XRD, right? There is this guide laser. All right. Yes. 영재 학생 감사합니다. 네. Yeah. Yes, cherish, right? Ramen on 라면이 아닙니다. Raman microscope, or there are some other tools. They use visual spectrum light. So we usually use red, green, or blue laser, right? 그래서 뭐 레이저 많이 하시는 분들은 뭐 532, 뭐 614 이게 딱 정해져 있습니다. The wavelength of light is determined. So let's say that we pick a green light, which has 532 nanometers of wavelength. Okay. Planck constant is a constant. Speed of light is constant. The only changing is the wavelength. And this is the electron volts. So actually, so this is wavelength. This is energy. Right? We know it has an inverse relation, right? Okay. So let's say for midterm, if I give you a value of a laser, right, or the wavelength of the laser, I can ask you what is the energy of that light, or I can give this energy first and then let you calculate the wavelength. And then by looking at this table, you can pick, oh, this is red, this is orange, this is purple, right? Okay. So if I were you, I'll put a big star in this slide, okay? And pay extra attention when you are studying for the midterm. Okay? 자, 중간고사 공부하실 때 이 슬라이드를 꼭 기억을 하세요. 아주 간단하지만, 그죠? 제가 이렇게까지 말씀드렸는데 중간고사 때 틀리면 저 정말 속상합니다. 오케이? 지은 학생 표시했어요? 아, 네. 지은 학생 넘버 2가 4학년인가요? 3학년인가요? 아, 네네, 알겠습니다. 두 분은 서로 아시나요? Do you guys know each other? 이번 기회를 통해서 좀 친해지면 재밌겠네요. 오케이. 네. 선배 지은 학생이 잘 좀 챙겨주세요. 커피도 한잔 사주시고. 자, 특별히 같은 조에 넣어드리도록 하겠습니다. So like, yeah, this example, but the color of light depends on photon energy. It also depends on optical properties of the reflected surface. So if you look at here, red or infrared has lower energy than purple. Okay. So we put sunscreens, and usually when you look at them, they like sunlight proof, whatever SPF, I don't know, where anyway it's like 35 or something, and it says a UV protection, right? If you go to Olive Young, right? 신미나, right? 신미나 이렇게 광고하는 거 있죠, 그죠? Right? So it has UV protection, right? So you might be wondering, okay, why don't there is IR protection? IR, infrared, 적외선, has a lower energy than the visual light spectrum, and our body is okay to the visual light spectrum. We can handle that power or energy. But ultraviolet has higher energy than this visual light, so they are harmful. Okay. Yes, Cherish. Yes, and also IR has lower energy, but they have higher wavelength, and they actually, our skin, right, is transparent, right? It is transparent, but it blocks a lot of visual light spectrum. 자, 여러분 지금, okay, you guys have a cell phone, right? Turn on the flash in your cell phone. 핸드폰 후레쉬를 켜세요, right? And then try to block it with your finger. 그죠? 이렇게 엄지를 한번 감싸 보세요. 잠시만요. 약간 고등학교 수업 같이 되는데, 자, 이게 재밌어서 그래요. 수업을 설명을 드리려면, okay? What color is your finger right now? 손톱 부분을 한번 보세요. 손톱 부분, 손끝 부분. What color is your finger? Red, right? Okay, red, right? What color is your flash? 여러분 핸드폰에서 나오는 빛이 무슨 색이에요? White, right? White red means that it contains all RGB information, right? White light, right, contains all these different color information. That is why, even though the light bulb in our room is white, and hopefully you have a light bulb in your room, okay? 뭐, 그쵸? 다들 전등이 있죠, right? The source of the light is generally white, but you can see blue, purple, right? You can see the red, you can see your screen, right? You can see all these colors, right? That is because the light source has all these color information. Okay. However, when you did that flash through your finger, right, you only saw red. That means that only red light has passed through your finger. Which means that in our body, right, light with lower energy can penetrate and go through. Okay. Okay. So you can consider that, right? So you can see that, okay, so infrared or high frequency, high wavelength red light can go through body. That is why when you go to this Oriental medicine or Oriental hospital, 그 한의원, right? 그죠? 침 맞을 때 전구 키죠, right? There is this light bulb of red color, right? Okay. 그냥 뭐 폼 하려고 한 게 아니에요. That is because you want to transfer this warm light energy deep into your body to maximize the effectiveness of the treatment. 그죠? 자, 침 맞을 때 괜히 빨간 전구 하는 거 아닙니다. 몸에 들어갈 수 있어서 그런 거예요. 오케이? 오케이. 솔직히 지금 조금이라도 한 사람 손 아니면 이미 아는 건데 왜 저러고 있지라고 한 사람은 손 안 드셔도 돼요. 오케이. 네. 다희 학생 감사합니다. 오케이? 네. 다들 okay. I think there is only good students in my lecture. I'm very lucky. 네. 착한 학생들밖에 없는 것 같아요. 네. 지금 손 안 드신 분들 다 기억하겠습니다. 네. Okay. Anyways, right? So that is the concept here. So yeah, I mean, sorry about talking about this medicine, but yeah, I mean that is the basically a concept. Okay. So when we talk about the nanoscale or when we do any research, right? I believe that all of you have any sort of experience with microscope, 그죠? Right? 여기서 현미경 안 써보신 분 없죠, 그죠? The most common form of 현미경 or microscope is this one. Okay. Right? Probably you have something like this in your lab, right? This type of 현미경 uses the visible light spectrum. It's an optical microscope, right? And it uses the light source of halogen or LED, right? And you are basically seeing the object based on the reflected light. The visible light microscope is in visible light spectrum. So their wavelength is 300 to 600 nanometer, and it has relatively low energy. Okay. So the light going into your sample in this microscope has low energy, so you don't really have to worry about damaging your sample. Okay. Okay. And then there is this X-rays, right? X-ray crystallography, right? They use a very high energy. I mean, we know that X-ray has high energy. They have much shorter wavelength. Okay? Half to 1 nanometer or 5 to 10 angstrom. And then there is this electron microscopes, right? I believe many of you are using SAM, TAM, and so on, right? Okay. These are the electron microscope, and we know that they can see very, very small scale, or few nanometers, easily, right? TAM can even see sub-nanometer object. Then you might be wondering, why are there so many different types of microscope with different light sources? So if you look at here, you can see a clear resolution difference between a general optical microscope and the TEM or SEM images. Usually the electron microscope has much, much higher resolution. That is because the light source that we're using has much shorter wavelength. Let's say we have a 5 nanometer object. If the light has a weight of 300 nanometer, it will not notice this object, right? Because it's too small compared to its wavelength. However, for electron microscope, it has a very, very short wavelengths. So it'll definitely interact with this object, right? Okay. So that is why this optical microscope has resolution in the order of tens of microns or a few microns, right? And then we can see much smaller samples in electron microscope. But as you can see, in electron microscope, we use an electron or these photons at much, much higher energy, right? So this can damage the sample. So, and also there is a strict limitations on type of sample. Okay? Also, we need vacuum, so we need a lot of conditions, right? We'll learn why we need vacuum for electron microscope and later in this class, but this is the basic concept. So, 그래서 제가 또 이렇게 굉장히 또 기초적인 거 설명을 드리는 이유는 여러분들이 이제 실험을 하실 때 앞으로 이제 대학원을 가시거나 뭐 제약회사에 취직을 하시거나 그죠? 뭐 여러 가지 그죠? 뭐 보석 가공사가 될 수도 있고요. 여러 목적으로 현미경을 사용하실 수 있게 됩니다. 그죠? 근데 저도 한 석사 때까지는 sorry cherish, but I'll do this in Korean. 저도 석사 때까지는 어떤 샘플이 있으면 그 샘플이나 얘를 만드는 거에 급급해가지고 그냥 현미경에 넣고 막 봤어요. 현미경을 그냥 물체를 보는 용도로만 생각을 했어요. 도구로만 생각을 했는데 뭐 전혀 생각 없었죠. 왜 SEM이 더 작게 볼 수 있고 왜 현미경이 더 크게 볼 수 있고 왜 현미경은 컬러가 나오는데 왜 SEM은 흑백이고 뭐 전혀 개념 없이 막 썼습니다. 근데 한번 이제 석사 때 그룹 미팅을 하다가 지도교수가 너 연구 내용 발표 전에 너가 썼던 장비들에 대해서 설명을 한번 해봐라 라고 했어요. 그래서 막 신나게 했죠. 얘는 이렇게 볼 수 있고 얘는 이렇게 볼 수 있고 얘는 뭐 이거를 깎고 뭐 증착하고 그죠? 네. 근데 엄청 혼났습니다. 그대로 미팅이 종료가 됐어요. 그 이유는 제가 충분히 이러한 그 장비에 대해서 충분히 이해를 하지 못하고 단순히 도구, 그죠? 소위 말해서 우리가 쓰는 가위라든지, 그죠? 제독이라든지, 각독이라든지 그 정도의 도구로만 생각을 하고 원리를 충분히 이해를 하지 못했던 거예요, 그죠? 그래서 여러분들은 제 수업에서 언급이 되는 반도체 공정이나 이러한 물질 특성 장비뿐만 아니라 여러분들이 실제로 쓰시는 장비들에 대해서 물론 많이 잘 아시고 이해를 충분히 하시고 있겠지만은 조금 더 공부를 잘 하면 좋을 것 같아요. 그죠? 그래서 제가 조금 졸린 학생들을 위해서는 2분만 더 썰을 풀자면은 Sorry, cherish just 2 more minutes. 예를 들어서 여러분들이 나중에 이건 제 경험담입니다. 이제 삼성이나 하이닉스의 면접을 보러 가요. 그러면 이제 저 같아도 삼성전자 반도체 사업부, 삼성전자 메모리 사업부, 그죠? PS 제일 많이 주고 이 회사는 너무 가고 싶어. 석사 하면은 연봉이 얼마고, 박사 하면은 연봉 초봉이 얼마고, 과장 대우 해주고 너무 막 듣기 좋죠, 그죠? 면접을 딱 보러 갔는데 막 얘기를 했어요. 김혜준 씨의 장점이 강점이 뭡니까? 공정을 7년을 했고, 반도체를 다 만들었고, 그러면 이제 거기서 저는 제가 어떤 거를 만들었는지, 그죠? 혹은 어떠한 저널에 어떠한 논문을 썼는지 이런 거를 궁금할 줄 알았는데 되게 원초적인, 이런 장비도 써보셨어요? 그 장비의 작동 원리에 대해서 설명을 해주세요. 라든지 아니면 그런 장비를 쓸 때 이런 문제가 발생하면 어떻게 해결할 수 있을까요? 그런 거를 물어보더라고요. 그래서 제가 제일 첫 번째로 면접을 봤던 데가 그 삼성 TP 센터라고 테스트 앤 픽 패키징, 삼성전자 TP 센터였는데 그 면접을 잘 못 봤어요. 왜냐면 저는 장비 쓰는 거에 급급했지 막 원리를 잘 몰랐기 때문에. 근데 솔직히 그런 회사에서는 네, 여러분들 얼굴을 못 보고 막 얘기를 하니까 여러분들이 재밌어 하는지 재미없어 하는지 잘 판단을 안 서는데 뭐 아무튼 그 여러분들이 진짜 어떤 저널의 논문을 쓰고 어떤 연구를 했는지도 중요하지만 일반적인 대기업에서 여러분들을 뽑을 때는 그냥 특정 큰 기술, 주요 기술을 가지고 있느냐를 위주로 판단을 하기 때문에 그러한 기본을 잘 아시면 좋고요. 반대로 그러면 왜 좋은 논문을 써야 되느냐 혹은 왜 논문을 써야 되느냐라는 거는 논문을 이제 한번 쓴다는 거는 여러분들이 어떤 연구 과제를 계획을 하고 연구 과제를 실험을 진행하고 그 실험 데이터를 정리하고 그 정리에 대해서 analyze 혹은 디스커션이 들어가는 일련의 과정이기 때문에 우리가 예를 들어서 우리가 여기 누구야 뭐 선우 학생을 혹은 뭐 세연 학생을 뽑았다. 박석호 교수님 박석호 교수님, 왔어. 다 뽑았어. 그죠? 그러면은 여러분들이 연구 분야보다는 여러분들이 연구의 능력, 그런 거를 보기 위해서, 네, 이렇게 하는 거기 때문에, 뭐, 다 다릅니다. 여러분들이 포닥을 가거나 교수를 하실 거면은 뭐 다르겠지만, 뭐 회사는 이제 보는 게 있어요. 그죠? So yeah, I spent like 5 minutes talking about some 여담 or 뭐 어떻게 보면 뭐 라떼는 그죠? 이런 뭐 꼰대 얘기일 수도 있는데 뭐 아무튼 그런 게 있었습니다, right? So yeah, I mean that determines the resolution of this microscope. Okay, so please also keep that in mind. Okay, so yeah, so before we actually go, so that was a very short, sorry. So that was a very short explanation for the quantum mechanics. It's not done yet, right? That is the case of photon, right? And the light was the very first example. If we want to go into more detail and talk about electrons, more about photons, right? More about this energy exchange, adhesion, right? Self-assembly, all these nano phenomena, right? We need to understand the atomic structure in nature. So let's review the high school chemistry. Right? We all know that atom consists of neutral neutrons and positively charged protons, okay, and surrounded by negatively charged electrons. So when the numbers of protons and electrons are equal, then we can call this atom as neutral. If they are different, depending on their relation, we can say this atom is positively charged or negatively charged. So atom is nucleus plus electrons. The electrons or protons are electrically charged by this amount. Okay? And also the number of protons in nucleus determines the atomic number. Okay? So if we know, this has atomic number of 6, then we know that atom has proton of 6 and probably electron of 6 electrons, right? So that is atomic structure. So if you go into here, there is concept also called the atomic mass. The protons and neutrons have the same mass. It's very light, right? It's 10 to the minus 27. I cannot imagine how much this light. Okay. Right? I don't think we can. I mean, I'm not even sure how people actually measure this. Right? And then there is a mass of electron. Electron also has mass. It is also very, very small. Okay. So let's say the electron mass is about 1 to the minus 30. Okay. It is still 3 orders magnitude smaller than proton or neutron, right? So it can be neglected in atomic mass calculation. Okay. 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 So here, I mean, yeah, I mean, it has an atom has a structure number, right? The number above is the mass number, number below atomic number. Okay. So atomic number basically determines the number of protons, and it might have difference in the number of neutrons, so we might have different mass number. Okay. Okay. So in case of carbon, both 12 carbon or 13 carbon has the same property because they have the same number of protons. However, C13, the 13 carbon is much is more heavier. It's heavier because it has more neutrons. So here, from this weight difference, we know that electron is much lighter. 훨씬 가볍죠. 그죠? Okay. So this is why the electron can move around while proton cannot, because they are much lighter. So they are much more responsive to energy input. Right? Okay. Right? So here is the basic concept. Okay. So let's look at here. So let's look into more three-dimensional case for atom. Every atom have their own electronic structure, or right, they have this structure or organized shape of electrons, right? or organized formation of electrons. Electrons, right, are lighter, right? Okay, and they are repelling from this. Yeah, not repelling. Sorry, and there are. You can think of this electron like an orbiting planet, and you can think about this nucleus as a sun, right? Okay, and these electrons, in reality, they form a cloud around a nucleus, and this radius is only in the order of 0.5 to 2 nanometers. Okay, so this gives you an idea that atom size is in the order of single nanometers, right? Okay, so this is the general case. But in reality, the quantum mechanics tells us that this analogy or this image is not correct. Okay. The only certain orbits or shells of electron probability densities, electron probability densities are allowed. So what this means is that if we consider this layer like a shell, in quantum mechanics, electron can occupy a very specific distance between these nucleus. So let me correct this. Okay. In reality, that this picture is semi-right, right? Okay. But what I'm saying is that there is a specific position around the nucleus that can be occupied by an electron. And I also mentioned that in quantum mechanics, everything is explained in probability. So we can find out so we can calculate, the probability of electrons staying in this first layer is this, second is this, third is that, blah blah blah. Okay. Okay. So the shells are identified the principal quantum number, which can be related to the size of the shell, right? So first energy level, so N is 1. Second one is N is 2, N is 3, and blah, blah, blah. Okay? Okay. And if you look into this shell, they are broken into many subshells. So we will also learn about this concept later in this lecture, right? But they are called the second quantum number. Okay. And also there are two more quantum numbers that characterizes the state of these subshells. Okay. 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 But what I'm trying to say here is that in reality, there is a specific distance that electron can occupy, okay, which is governed by the law of quantum mechanics. So let's look into more detail here. So there is a model called wave mechanical model developed by Bohr, right? So this is the atom. Here's the nucleus. Right? And let's say this is the first shell. The probability of electron staying in this shell is given here. Okay. Electron staying here is very low. At this shell, it reaches maximum and then goes down again. So if you're in reality, a lot of electrons will be located near this um, yeah, near this shell. Okay. 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 Sorry. Uh, I got logged out from my tablet, so oh, actually, okay, it's very unstable, but I'll proceed, right? So let's look at what this wave mechanical model is. The electron is considered to exhibit both wave-like and particle-like characteristics. With this model, an electron is no longer treated as a particle moving in a discrete orbital, but rather position is considered to be probability of an electron's being at various locations around the nucleus. In other words, position is described by a probability distribution or electron cloud. Okay? So in high school, you probably have learned, oh, okay, my tablet is not working, so let me log in with my computer. Give me a second. Okay? So what this is trying to say is that that the electrons are gathered around this orbital, okay, and we can actually calculate the probability, right? Electrons staying in the orbital. Okay. So I'm logging in, okay, I'm here again. All right, now everyone can hear me, right? Okay, so what I'm trying to say is here is that everything is probability. So let's say you have an atom and you have two energy levels, and then you have, and then maybe you have, oh sorry, two energy level, and let's say you have three electrons. You have three electrons. The probability of electrons being in the first shell is 66%, and it is 33% on the second shell, and there will be 2 electrons in the first shell and 1 in the outer shell. Right? This is the wave mechanical model, and the way how to calculate all this probability, right? All those complex things, I believe that can be learned in more detail in quantum mechanics course. But that is the concept here. So why is this important? Okay. This is important because this probability or wave mechanics model, right, is directly related to the energy of electron in that level. 그러니까 한국말로 설명을 드리자면은 이 확률이 왜 중요하냐면은 이 확률이나 이런 모든 게 왜 중요하냐면은 각각의 에너지 레벨에 따라서 그 에너지 레벨에 모여있는 일렉트론의 에너지가 다릅니다. 그러니까 그 첫 번째 서클이냐, 세컨드 서클이냐, third 서클이냐, 이 모든 서클에 있는 일렉트론들이 가지고 있는 자체 에너지들이 다 달라요. Okay. In general, the energy of electron increases. Not in general, always. The energy of electron increases as the electron gets further away from nucleus. Okay? 자, 일렉트론이 힘이 없으면, 그죠? 얘는 네거티브 차지니까 포지티브에 더 끌려 들어가 있겠죠. 그죠? 오케이? 예를 들어서, 그죠? 이 누클리어스가, 오케이? 음식이라고 합시다. 오케이? 음식. 오케이? 네. 효진 학생, 김효진 학생, 네, 저희 그 디지스트 김밥 천국 가시죠? 제일 좋아하는 메뉴가 뭐예요? 혹은 제일 맛있는 메뉴? 아, 내가 김혜준한테는 이걸 꼭 추천해야겠다. 치즈라면이요? 네, 그럼 이게 치즈다, 오케이. Alright. Then let's say this is 치즈 ramen in the middle, right? And let's say this electron is Hyojin, right? When, as Hyojin has no energy, 효진 학생이 힘이 없고 배가 고플수록 치즈 라면의 유혹에 더 가까이 다가가겠죠. 그럼 고민을 하겠죠. 3일 연속 라면 먹었는데 안 되는데 이러면서 그죠? Alright? So that is the same thing. Right? When electrons has more energy, they get further away from this nucleus. And there is actually an equation that can quantify this energy as a function of energy level. So energy level is the measurement of discrete energy an electron can absorb when light or other form of energy strikes an atom. 그죠? 뭐 포톤이 될 수도 있고 다른 일렉트론이 될 수도 있고 다른 뭐 몰레큘이 될 수도 있고, right? When this energy enters into the system, some of these energy can transfer to the electron in this level. So when they gain such energy, they can make a jump to the second level. And they can make another jump to the third level. And they can make to the last level, right? Every atom has different number of levels, but in this case, we have 4, right? And then they can jump out. Okay. So how do we know this energy level? Energy of electron. Let's say this is the energy. Electron has some movement, right? And has this kinetic energy, right? So kinetic energy, the pure energy is from this kinetic energy. 1/2 times mass times velocity squared is equal to momentum squared divided by 2m, right? Momentum is P is mv, right? Okay. Momentum is Planck constant times the number of energy level divided by 2L. Okay? L is the characteristic length. Okay? L is basically the length that it has to travel, the length it has to overcome, right? The length between this energy level. Okay? So if you rearrange this, in many atomic structure, the distance between energy level is a fixed value. Mass of electron is fixed. Planck constant is fixed. So here what we can know is that, oh, the energy of electron purely depends on where it is located, in a first level or second level or third level. 이해가 가시나요? 아, 나 이거 진짜 모르겠다. 교수님 이거 너무한 것 같아요. 너무 어려워요 하시는 분 손 들어 주시겠어요? 아니면 교수님 너무 쉬워요. 저희를 얕잡아 보지 마세요 하시는 분도 손 들어 주셔도 돼요. 수미 학생, 영재 학생, 현종 학생 괜찮아요? Okay. 네, 민영 학생 감사합니다. Okay, L, okay, is the characteristic length L. Okay. So basically, L is the distance between these energy levels. So L is the distance that electron has to travel to jump over to that next level. 자, 아톰에 핵이 있고요, 그죠? 그 다음에 일렉트론이 첫 번째로 모여있는, 옹기종기 모여있는 첫 번째 껍질, 그 다음에 두 번째 껍질 이렇게 있죠, 그죠? 핵에 가까운 일렉트론이 그죠? 포지티브 차지에 끌려서 이렇게 있어요. 얘네가 있어. 근데 이 일렉트론이 에너지를 먹어. 이네 에너지가 생기면 어떻게 돼요, 그죠? 나 이제 에너지 생겼으니까 에너지가 넘쳐. 나 이제 뛰어넘을 거야. 근데 그게 이제 세컨 레벨로 가려면 한번 점프를 해야 돼요, 그죠? 자, 일렉트론이 조금 에너지 먹었다 그래서 이 포인트에서 이 포인트로 가지 않아요. They can only exist at the specific levels, right? So they need to make a jump. 이 점프를 해야 되는 거리를 L이라고 합니다. So when you actually have to solve this system, depending on atom, 뭐 어떤 물질이냐에 따라서, 혹은 depending on the structure, this L value is generally given, and it's in the order of nanometers. Okay? Sure. 네, 민영 학생 감사합니다. 네. 항상 감사해요. 렉처 노트도 확인해 주시고 많이 감사하고 있습니다. Okay? Alright. So if I were you, I'll also put a big star in this equation and this concept, and I'll take a close look when you are studying for your midterm. 자, 렉처 5의 12번 슬라이드를 별표해 놓으셨다가 중간고사 때 한번 보세요. 이 식을 외울 필요는 없어요. 오케이? 시험 때 제가 이 식을 드릴 겁니다. 식을 쓰셔야 되면, 그죠? However, right, you'll have to understand this equation to solve a problem, right? Okay? 그죠? 이렇게까지도 설명드렸는데 중간고사에서 틀리면, 그죠? 김혜준 교수가 굉장히 슬플 겁니다. Okay? Alright, so that is the case. So yeah, so there is a concept of potential barrier. Let's say there is a given spot, and let's say this is 예린. 예린 학생 여기 있어요. 예린 학생, right? 여기까지 가야 돼. right? 그러면 총총총총총총총총총총총 걸어가면 갈 수 있겠죠. right? 근데 여기 사이에 있을 수가 없어. By wave mechanics law, this part cannot be occupied by electron. So Yerin has to make a jump. And between this energy level, there is a gap of energy. 자, first energy level과 second energy level 사이에는 극명한 에너지의 차이가 존재합니다. So when Yerin has energy equal to this delta E or higher than this delta E, then she can make a jump to the energy level. Okay, and you can think about this energy difference as a potential barrier. 뭐 허들을 뛰어넘거나, 그죠? 아니면 뭐 그 여러분들 그 국민학교 때, 아니 초등학교 때, 그죠? 이거 뭐라 그러지 이거? 이렇게 뛰어넘는 거 있잖아요, 이렇게 뛰어넘는 거, 손 짚고 폴짝. 그래서 막 엉덩이 찌고 막 넘어지고 깔깔대고 이랬다. 뭐였죠 이거? 뭐였지? 이거 뭐였죠? 뜀틀이에요? 뜀틀. 도마 아닌가, 도마? 뜀틀? 그죠? 네. 기억이 납니다. 그죠? 네. 그죠? 네. 요즘도 하나요? 이거 학교에서? 안 하나? 수미 학생, 중학교 때 했었어요? 네. 네, 알겠습니다. 네. 오케이? 그죠? 이런 뜀틀을 생각을 하시면 돼요. Right? The electron has to gain a certain amount of energy to jump over to the next level, and that potential barrier or the energy barrier is equivalent to the energy difference between these two levels. Okay? In quantum mechanics, a very small portion of carriers, 극히 일부분의 캐리어들은 이거를 그냥 뛰어넘어갈 수가 있어요. 아주 특이한 케이스에 따라서. That is called the tunneling effect. Okay? But the majority of electrons or carriers will be blocked by this potential barrier. But there is a very slight chance they will go through this potential barrier. And that chance or that probability can be also be solved by using this quantum mechanics. Okay? 그래서 이런 터널링 이펙트도 아마 제가 드린 리딩 어사이먼트 안에 설명이 좀 더 들어가 있을 겁니다. So let's think about this. The interaction with phonons. Right? In phonons, we have learned that energy of phonon is equal to Planck constant times the frequency of the light, or Planck constant times lambda times speed of light. Okay? So let's say these energy gap is certain volume. Okay. And then, so when this electron comes down from the second energy level to the first energy level and gives out the energy equals star, that energy, some of that energy can be expressed in form of light, in photon energy. So this barrier energy difference, star equal to h frequency, right? So if you know this energy value and divide this by Planck constant, then you can get this frequency, okay? Or you can get the wavelength. So you can guess the color, right? 그렇죠? 그래서 제가 중간고사 응용 문제를 낸다면 뭐 여러 가지가 있겠죠, 그죠? Right? If this is 1 electron volt, what is the color of light when electron drops from energy level 2 to 1? Okay. Or actually, you can calculate this E1 or E2 using this equation right here, right? So by mixing all these, many things can happen, 그죠? 숙제로도 비슷한 거 하나 내드릴게요. Okay? Or if a certain material receives this light energy, and if they absorb this light energy, this electron will jump over to the second level. Okay? So by applying light, you can excite the electron, or by controlling this electron going down to the lower level, you can generate the light. So LEDs, light emitting diodes, is a material that does this process. And for this specific LED materials, the given out light wavelength is in the range of visual light. Okay, so this is the concept of electron proton interaction, and this is the very introduction or very basic of the foundation of the quantum mechanics. Okay? So when you are shining a light, you are actually giving energy into the system. Okay? Okay. So um, yeah, I mean, this next slides will take some time, so I'll stop here. Yeah, so my apologies for not finishing the lecture today. Okay? 뭐 중간에 약간 수다도 떨었고요, 그죠? 근데 예, 뭐 여러분들 그 아무래도 좀 그 대면 강의 때보다는 온라인 수업이 조금 더 듣기 어려우시죠?